Yeah, so the key is yeah, the key is that there's some kind of infinitesimal thing going on. And somehow when I take an interval of values, all of those things that were zero end up adding up to give you something. There's like, you guys ever watch the on YouTube, there's like Numberphile. You know what Numberphile is?
Yeah, I love those videos.
Yeah, there's one on infinitesimals in there that's pretty interesting. And it talks about this exact thing. You can go, I would recommend going and checking it out. Newton and Leibniz, who invented the calculus, had, or were the first ones to really discover that something was going on with these infinitesimals, that they weren't exactly, zero, even though we treat them like zero. But a lot of this stuff hasn't even been made rigorous until the last, 30 years or so, 40, 50 years. So there's a Numberphile video called, I think it's called, it might be on the reverse. I think it's called The Reverse of Infinity or something like that. I can't remember, but it's a pretty interesting little video that talks about this exact thing, Timothy. Yeah. Oh, did you find it?
Yeah, I found it. I just put it in the chat.
Yeah, there it is right there. The reverse of infinity. Is that what was it called? The reverse of infinity?
The opposite of infinity.
The opposite of infinity. Okay, yeah, there you go. I've gone down plenty of rabbit holes on that website. Yeah, some pretty cool stuff there. Well, what other questions? And by the way, these are great questions. Um, I I just have to be careful about what I spend time on in the lectures themselves because because you could definitely go down a lot of rabbit trails here for sure. So yeah, but I'm glad you guys are kind of seeing some of the tricky nuances for sure. What else?
So, what does this example like represent? Is this like the bus like waiting at a stop or something? And like, what's the distribution of that?
Well, I mean, that was just meant to be like a practical situation where if someone arrives at like a random time, they don't really know exactly when I mean, they may not know exactly when the bus is going to arrive. They just know it comes every 15 minutes. So the probability that they're going to have to wait any amount of time between 0 and 15 minutes is basically the same. Does that make sense? Since from their perspective, they have no clue when the bus is going to arrive. So it makes sense that you would model that with like the uniform distribution on 0 to 15 or something. I didn't go into a lot of details on that one. I just wanted to give you a situation where you basically have, a uniform distribution arising naturally. Yeah. By the way, I didn't talk about it explicitly, but there is a uniform distribution in the discrete case also. Like for instance, like rolling a die. If I rolled a die, the outcomes are 1, 2, 3, 4, 5, or 6, correct? And what's the probability that any one of those outcomes will happen?
1/6.
Yeah, a sixth. And it's the same everywhere. So that's called the uniform distribution in the discrete case. Okay. We didn't spend really any time on that, but that's a fairly intuitive distribution. It's just a little trickier in the uniform case because you're not used to all this integration stuff. Other questions? Other questions?
How would this be used to compute batting averages?
Well, I mean, I don't know that I would use uniform distribution with batting average situation. I mean, because I mean, I don't know if that's the accurate distribution, but we were more talking about. I think that example was like data. Batting averages are continuous data. Does that make sense? So technically speaking, a batting average could be anything, you know, between 0 and 1, in essence. Okay, so that's continuous data. The way we record batting averages, we only keep track of to the thousands position, right? So the way we record batting averages makes it seem like actually discrete distribution, like a discrete situation. But technically it's continuous data. So that was just an example of continuous data. What else? Any clarifying questions on on the exam? Which is due on Wednesday. By the way, I'm not going to, you know, I'm not going to govern any of this, obviously, but I made the number 3 questions on the first page all possible to do by hand. Okay. In fact, I did them all by hand, like in like not very long, just a few minutes. Okay. So they're all possible to do by hand. You shouldn't even need a calculator, although I won't, you know, I didn't sort of say you couldn't use a calculator. But if you feel like there's some kind of unwieldy computation going on, then you're probably not looking at it right. So that's just a word of warning there. Okay. Anything else? Anything else? Well, thanks for coming in and asking some good questions. I'll try to have the lecture up sooner than the day of for Wednesday. Apologize about that. I got really bogged down this weekend with grading, so stuff just kind of piled up. So hopefully I'll get back into a better groove here pretty soon. So for Wednesday, I'm going to talk about the exponential distribution. I'll do another example involving the uniform distribution. The exponential distribution is important in actuarial science, which is those guys that determine how much to charge you for your insurance, like your car insurance, house insurance, that kind of stuff. So I'll deliver a lecture on the exponential distribution, which is connected to the Poisson distribution, which we've already talked about. And then that will finish chapter 5, and chapter 6 is purely the normal distribution. And once we have the normal distribution in our back pockets, we're going to be able to do some pretty sweet stuff with statistics. Okay. So that's where we're headed. I won't give a homework quiz this week, but by Wednesday, I'll put up like a, you know, a set things to work through in the Alowski-Dean text. And probably a week after, maybe a week from Wednesday or something, I'll have a take-home quiz for you to work on that will be related to those problems from Alowski-Dean. All right. Any other questions?
Is the normal distribution the most commonly used, or what we use the most?
Yeah, but there's a reason for that. And it's not because everything is normally distributed. That's not true. But it turns out that in most of the ways that we collect data and interpret it, it turns out that the questions we tend to ask basically allow us to assume some kind of normal distribution is going on. And that's going to be related to something we call the central limit theorem. So basically, you don't even need to know what the underlying distribution is. If you ask the right question, you can assume that stuff is normal. So that's a miracle. And that allows you to be able to say a lot of pretty rigorous stuff statistically about data that you collect, which is amazing. Anything else? All right, well, thanks everybody. Have a good afternoon.
Thank you, Dr. Hammond.
See you soon.